the mic, or where am I speaking to?
So this will pick you up for here, and then we have this, which will head back. Or you got your clicker. See if I can do this off the top. All right. Our next speaker is Professor Michael Manfra. He got his PhD from Boston University in 1999. And then, note. I forget what he posted.
I was a postdoc and spent 10 years as a member of technical staff at Bell Laboratories.
That's correct. Sorry.
Yeah, Murray Hill, New Jersey, not too far.
Great. And today he's going to be talking about direct observations of anionic braiding statistics. Welcome.
Okay, thank you for the invitation. This is going to be an experimental talk. I'm going to try to tell you about our efforts and work that is allowed for observation of anionic braiding statistics. Tell you a little bit about the theoretical motivation behind it, but really the talk will, and one tomorrow, will be about overcoming some of the experimental challenges. They wonder why it took 40 years to measure anionic braiding, and hopefully this couple of lectures will give you a feel for that. Okay, so now it doesn't work. Worked a minute ago. Okay. All right, so you all know that the elementary particles in 3+1 dimensions come in flavors of fermions and bosons. And the distinction between these, the statistics is important. It determines a lot about the properties of materials that are comprised of either fermions or bosons. So we know spin 1/2 particles are fermions and obey the Pauli exclusion principle. They cannot be in the same quantum state at the same time. And if we interchange particles, exchange particles, the wave function picks up a factor of -1. Now, using the statistical properties and some symmetry arguments of fermions, you can describe much of solid state physics. So, statistics is extremely important to the foundations of condensed matter physics. Similarly, bosons behave quite differently. They can, of course, be in the same state, quantum state, integral spin, and of course, when you interchange two particles, you get the same wave function back. And of course, there's very dramatic demonstrations of the properties of bosons, Bose-Einstein condensation, superfluidity among them. Now, in the late 70s, early 80s, it was realized that at least in 2+1 dimensions, another type of excitation, maybe not necessarily a fundamental particle, but emergent particles in two-dimensional systems can have properties, statistical properties, that interpolate between fermionic and bosonic, and these were deemed anions. Frank Wilczek coined the term. And these excitations that occur in certain strongly interacting 2D systems can carry fractional charge, a fraction of the ferroelectronic charge, and have fractional braiding statistics. When we take one anion around another, we pick up a phase factor that is neither 1 or -1, but given by some complex fraction. And as it turns out, the fractional quantum Hall effect that was discovered almost concomitantly with the generation of some of these theoretical ideas is a perfect platform for investigating and trying to realize anyons. So as we'll learn in today and tomorrow, the quasiparticles in the fractional quantum Hall state, I'll specifically focus on 1/3 today, as it's the strongest, the most well-established state, carries fractional charge. The excitations, the quasiparticles, have a fractional charge of E/3 and have fractional braiding statistics. The statistical angle for braiding is 2π/3. And the fact that we have a system in nature where we can actually realize this is, I think, a really unique opportunity to explore some concepts that may have more general applicability to other less understood condensed matter systems. So where does this all come from? Well, already in 1983, Laughlin's original theory of the fractional quantum Hall state as an incompressible liquid with fractionally charged excitation went a long way to telling us what was going to be important. The sort of the central feature of the Laughlin wave function, at least at 1/3, it's right down here, I'm sure everyone's seen it, is it puts 3 zeros at the position of each particle. Charge and vortices are tied together. There's just this very strong connection between the vorticities in the wave function and the location of charge. And as we're going to learn, this type of description lends itself in certain models to a description of anyons. Now, of course, in Laughlin's original paper, he already predicted that the charge of the excitations was E/3. But shortly thereafter came notions that they were not only the excitations were not only fractionally charged, but they were indeed anyons at fractional statistics as well. And so there's sort of a confluence of different ideas in a somewhat, it may seem a toy model or a bit of an abstract construction. Wilczek in '82, remember the fractional quantum Hall effect was '82 as well, considered a model of composite particles where charge is tied to vortices in 2+1 dimensions. And he worked out the quantum mechanics and found that these composite objects of charge and vortices could have fractional angular momentum. Their fractional angular momentum, then their statistics can be fractional as well, interpolating between fermions and bosons. And he worked out the two-particle quantum mechanics for this in some detail. And I always find it interesting to look at these somewhat maybe parenthetical statements. Although practical applications of these phenomena seem remote, they have considerable methodological interest and some light on the fundamental spin statistics connection. So you see the paper was received in, June of '82. The first quantum Hall data, fractional quantum Hall data was coming out. Laughlin soon came out with his theory, and then Bert Halperin shortly thereafter, at the end of '83, in trying to develop a description of higher order states from 1/3, say 2/5, or other states, noticed that the quasiparticles of the fractional quantum Hall effect will obey fractional statistics, just like envisioned by Wilczek. And he notes the appearance of fractional statistics in the present context is strongly reminiscent of the statistics introduced by Wilczek to describe charged particles tied to magnetic flux tubes or vortices. And of course, this is at the foundation of our present understanding of the fractional quantum Hall effect. And it was interesting to see just how quickly all these ideas were coming together. And shortly thereafter, basically using the adiabatic theorem techniques that modern students would understand now, or Provost, Schrieffer, and Wilczek also calculated that if you take one quasiparticle around another, it will engender fractional statistics as well. So note, by 1984, the key ingredients of the fractional quantum Hall effect are there. It's an incompressible quantum liquid, fractionally charged excitations. They also should have fractional statistics as well. And of course, it's taken us a long time as experimentalists to come to a point where we can say that these attributes are clearly demonstrable in experiments. And that's sort of the story I'd like to tell you. Now, of course, in modern samples, and if you're just doing bulk transport measurements, the quantum Hall effect is pretty easy to understand. You have a slab of a 2D material. In this case, it's aluminum gallium arsenide heterostructure. You drive a current through it. You can measure the transverse or Hall voltage, the longitudinal voltage along the direction of current flow. You cool the sample down to low temperatures. Case here from some data earlier this year from my group at 10 millikelvin, and you apply a large perpendicular magnetic field, and you see the familiar characteristics of the linear Hall voltage interrupted by these plateaus, which are precisely quantized to not only integer values, which obviously has to do with the single particle spectrum breaking up into lambda levels, but fractional values, 2/3, 3/5, 5/2 as well. And where the Hall voltage is precisely, or Hall resistance is precisely quantized, the longitudinal resistance drops to 0. And so you'd say, well, okay, maybe that's all you need. But in fact, actually teasing out, at least experimentally, that the excitations, the charge is 1/3 in the case of 1/3 state, wasn't so easy. It took the development after the original theory about 15 years in development of samples and quantum shot noise experiments for the charge to actually be measured in a series of experiments of the Weitzman group and also at Seclet in the late 90s that demonstrated that indeed charge is carried in units of E/3. So that was a 15-year development. A lot of experiment, both materials and experimental techniques had to come. Now, as I mentioned, anionic braiding statistics, the anionic phase, at least for the Laughlin states, is a simple 2 pi E star over E, the ratio of the fractional charge to the Baird charge of the electron. That was also known very early on, but I'm giving you a talk about this today, and it's only been the last few years that we can say with some degree of certainty that we have measured these properties. And just to be clear what I mean, I'm going to let these little spirals, these little vortices, these cartoons represent quasiparticles. And what I mean is if I take one around another and bring it back to its original position, you'd say, well, that's trivial. You're back in the same state. There's nothing to be known about that. The fact that there is actually a measurable, observable associated with this operation is kind of pretty interesting and not obvious. And of course, the extensions from the abelian case to the putative non-abelian states is even more interesting, if you will, that you can rotate the system within a degenerate manifold has created quite a lot of excitement. But in any event, I'm going to tell you about measuring abelian phase and trying to find operations in real systems that mimic this cartoon I've just shown you. So again, I just want to emphasize we're going to focus on filling factor 1/3. In this particular case, the anionic braiding phase is 2 pi over 3. Right. So how are you going to measure these properties? It could be argued that the quantization, the Hall conductivity, is the topological invariance of seeing quantized. Hall effect or Hall conductance is in a way a measure of the charge, but measuring charge directly took a lot of work. But how are we going to measure statistics? That seems even less well connected to things that we can do in the laboratory. But in 1997, Shimon and co-workers, some of whom are in the audience this week, developed a theory of what we now call a Fabry-Perot interferometer, or this electronic analog of Fabry-Perot interferometer. Fabry-Perot, of course, interferometers and optics have been around for quite some time. And basically, they designed conceptually a two-point contact interferometer in which we can partition currents and have them interfere. And this interference, as measured through conductance measurements, will allow us to see the anionic contributions to the phases that are developed. And I just want to point out, this is back in '97, there's a lot that can be done with electronic interferometry. It may be hard to read, but what they actually claim in the paper, and it turns out to be true, that the interferometer can be used as a means of measuring charge of quasiparticles, the statistics of quasiparticles, and by looking at the properties, the nonlinear characteristics of the edge states, you can extract Luttinger liquid parameters and behavior from the chiral edge mode. So in this paper, sketched out a lot that can be done in this particular experimental geometry. A lot of information can be gleaned. And again, you'll see the date, this is 1997, and you could say, well, what took so long? So that's the story as an experimentalist. I'm going to tell you now what took so long, what was hard, and what we learned along the way. So it turns out that Fabry-Perot interferometry, this two quantum point contact interferometer, does allow for direct observation of anionic braid statistics and more, as it turns out. And over the past several years, been fortunate enough that my group has been able to play a significant role in this exercise, going back to starting around 2018, but in 2019, we came up with a structure that would allow Aronov-Bohm-like interference patterns to be visualized. I'll tell you what those are in a moment. Then in 2020, through modification of this heterostructure and device design, we were able to directly see phase slips associated with the removal or addition of quasiparticles, and those phase slips were in line with the braiding phase of 2 pi over 3. And more recently, we've been able to take those structures and not just sort of luck out when you see the impact of anions, but we can actually control them by design. We can modify the devices so that we have a rather fine control over the properties of the interferometers, and they can be used in other regimes that allow us to see the impact of anions where you would not necessarily have at first thought you'd have them. And most recently, this has been extended to higher order, more complex fractions, nu equals 2/5. And you may say, well, okay, you did 1/3, why is 2/5 interesting? Well, we picked 1/3 because it's the easiest. The fact that we can do this at complex fractions that have multi-modes, multiple chiral edges, and we can individually interfere the different modes is an important step, and extract the statistics in a regime where charge, phase, and filling factor are not all the same, bodes well for future experiments where we might also be looking at complex states such as 5/2. Okay, so how does this thing work? This will be simple, everyone can understand. Think of the blue region as the two-dimensional electron gas. These sort of, I don't know, straw-colored S and D contacts are the source and drain. That's where we source the current, or where we drain the current out. These yellow lines here are surface gates. They sit on top. We put voltages on those to deplete the electrons in the 2-dig underneath those gates, and they define the interference path. So in the surface gates define the path, And the quantum point contacts, these two, these skinny arms that extend in and have a gap there, one out near the source and one near the drain, are used as the beam splitter. They're the electronic analog of the optical beam splitter. We use it to partition the edge currents. So in the quantum Hall regime, current is carried by the chiral edge modes. It comes into the first beam splitter, the first QPC. We can backscatter a certain amount of that edge current. That's under our control. Most of the current continues on through the interferometer. At the second QPC, we again choose how much to backscatter current. That current, shown by the dashed line, circulates around the interior interferometer and, of course, interferes with the part that was backscattered at the first QPC, while most of the current continues on to the drain. And by looking at the modulation of the drain current, how it changes as a function of system parameters, we can use that to extract the interference phase, which is directly related to the anionic phase. So the way this works is that the current, the backscattered current, or rather in this case the transmitted current, depends on the transmission coefficient amplitude squared of the first QPC, the second QPC, and of course there's a cross term, cosine theta, that is this interference term of the at least in the integer state, the electrons circulating around and interfering with themselves. Now this theta is the interference phase of the interferometer. It's not the anionic phase yet. It's important to keep those separate, but you can see how this works. If I'm just in, say, the integer quantum Hall regime, and my fundamental excitations are bare electrons, then the phase that develops as I go around this loop, remember it's pierced by a magnetic field pointing into the page, will be nothing other than the Aronoff-Bohm phase. The Aronoff-Bohm phase is proportional to the area times the magnetic field, that's the flux, and it's periodic in units of phi naught, the fundamental flux quantum, h over e. So if I just have electrons going around, I'd expect my conductance to be modulated periodically, depending just on the Aronoff-Bohm phase. Now we can measure the interference by measuring electrical conductance across the device. We can operate the device in a couple different ways. These side gates here, these big T's, we can think of them as plungers. We can squeeze down on the area of the interferometer, and we can make it bigger. We can play the accordion with those gates. We can also, of course, change the magnetic field, how much magnetic field we're applying perpendicular to the system. So we can change the area by modulating the gate voltages, or we can modulate the flux by changing the magnetic field. And naively, you expect lines of constant phase or constant conductance to have negative slope in the BVG plane. I'm going to make a bunch of two-dimensional plots where on one axis is the magnetic field, how much we change that. On the other axis is the gate voltage that we're using to change the area. So very simply, if you're just dealing with electrons, you'd expect these barbershop-like pole pattern to develop where a single color, red, is a constant value of conductance or phase, and you have oscillatory behavior because of the AB effect. Now, if I go to the fractional regime, things become a little bit more interesting. Say I'm representing the fractional regime in this cartoon by putting a localized quasiparticle in the interior of the interferometer. The first thing that happens is that the Aronoff-Bohm phase gets scaled by the effective charge. So at nu equals 1, if you had a periodicity of 5 millitesla, at 1/3, it would be 3 times that, because we effectively scale the AB phase by the effective charge. So there's a way of actually getting the charge out. But most interestingly, this interference phase depends on the number of localized quasiparticles, those guys that are trapped on the interior of the interferometer, and it depends in two ways. One, on the number, but also directly on the statistical phase angle itself. Okay, so you could imagine if I change the number of localized quasiparticles, remember that has to be integer. I can either add one or remove one. I can't remove a fifth of one. I might see discrete phase jumps or phase slips in this type of pattern. I'd have AB-like development, but if I removed one anion or added one, you could see a glitch. You might think it was noise, but it's actually a phase slip. And that phase slip would tell me directly about the anionic phase itself. And if I can use that, get that in my measurements, I can have direct access to what the phase, the braiding phase is in any particular correlated state. Okay. So, a lot of this was laid out in the pioneering paper of Shimon and collaborators, but a lot of the gory details about what goes wrong and what can you expect in different regimes was worked out later by Bert Halperin and collaborators. And these papers are ones that we rely on to really try to understand what's going on in our system. Okay, so what's the problem? It sounds trivial. Why am I talking about this 40 years after the original idea was put forth? And well, it turns out life's not so simple in the real systems. And while you have this expectation, say we're just in the integer regime of lines of constant phase with negative slope in the magnetic field or the flux gate voltage space, what you see in reality and for a long time in experiments was something very different. If you look at small interferometers like the cartoon I showed you but built in gallium arsenide systems, you would see some periodicities and lines of constant phase, but they were sloping the wrong way. They're just going in the wrong direction. And this was seen time and time again. And it actually comes down to a very fundamental issue that these interferometers that I'm describing to you, I describe them as ideal inert interferometers, but they're mesoscopic devices. They're not that large. They're like quantum dots. And all sorts of mesoscopic physics gets involved when you're trying to build these things, like charging energies. There's a charging, a self-capacitance for putting charge on and off such a device. There's an interaction between the chiral edge mode circulating around the periphery and the charge in the bulk of the interferometer. That's called the bulk edge interaction. And the problem is this makes it, in some cases, impossible to observe any effects related to statistics. This bulk edge interaction causes the area to change with magnetic field. It's like the interferometer is a living, breathing thing. It's not static. So you increase the magnetic field, but in order to find the minimal electrostatic energy configuration, the interferometer actually shrinks and the edges grow in. And so even though you've increased magnetic field, the flux actually decreases because you shrunk the area. This is happening so that the system can minimize its overall energy. So what happens, at least in the early days, is that you can't change the area and the magnetic field independently. Flux decreases when you increase magnetic field. Why is this a big deal? Well, in principle, it makes braiding unobservable. If you have this strong coupling, the system compensates just enough to actually cancel out any anionic contribution, and then you'll just get multiples of 2 pi. Okay, so this was a serious roadblock, and it wasn't completely understood for quite some time. And so this is one of the serious challenges that has faced the community. Okay, in fact, Bert, Halperin, and others have really gone into some gory detail about what kind of spectra you can see depending on the range of the self-capacitance, this bulk edge interaction. And you can go all the way from this AB regime, now I'm talking mostly about integer states that I showed you ideally, all the way to something that's called the Coulomb-dominated regime, the one I showed you in practice, where the lines are going the wrong way, and you can get all sorts of intermediate behaviors, checkerboard patterns, that tell you something about the interaction parameters of your interferometer. And specifically, the regime of operation depends on the ratio of some coupling constants, KIL and KI. So KIL parameterizes the bulk edge interaction. Okay, that's an energy scale. Ki parameterizes the energy cost to add charge to the edge. It's like the edge stiffness. How much penalty do I pay to add charge to the edge? And depending on that ratio, you can be in anywhere along this spectrum. And as I said, it's really important because if you're too far into the Coulomb-dominated regimes, you cannot see the phase change associated with the parading. You just get multiples of 2 pi. Okay. So what did we do that allowed us to get into a workable range? Well, we looked at some of the early pioneering experiments by other groups that got part of the way. So one telling one was work from Charlie Marcus's group. And what Charlie did is he made 2 types of interferometers. He made a small one. By small, it has a 2 micron square area, and it has a surface gate, this big gate on top, metal. And then he made a large one, which is huge by quantum dot standards. It's 18 microns square, and it also has a top gate. Okay, so if he makes it small, well, bulk edge interaction, this charging energy, a small object has this capacitance that it causes it to take energy to put charge onto or off of the interferometer. And in that regime, with these small devices, he got what we call Coulomb-dominated behavior, the one we don't want. And this is an example of Coulomb-dominated behavior. And no matter what he did, he couldn't change that. But he found something interesting. If you make the interferometer very large, huge by quantum dot standards, you reduce the charging energy, you reduce these Coulombic effects because it's so large. And combine that with the top gate, at least in a very limited range, he was able to get AB-like oscillations where the slope of the lines of constant phase point in the right direction. But no, the field scale, he's working down at half a Tesla. This behavior all fades away at higher magnetic fields, and this is not in the interesting quantum Hall or fractional quantum Hall regime. In fact, it would be approximately 20 or 22. And what price did he pay? Well, making it big, there's a large perimeter, and he's very sensitive to decoherence. There's the edge state that has to circulate around without decohering in order to produce interference. And by making it big, he quenched the charging energy, but he really lost the coherence. And so what we needed to do was find a way to make the device still small, so it's high coherence, but really quench this charging energy or bulk edge interaction that was plaguing the smaller devices. And one hint was, well, you put this gate on top. What does the gate do? Well, you can say I'm controlling the 2-deg density, but it also acts as a metal plane that's potentially not that far from the 2-deg and can help screen the Coulomb interactions. Okay, it just wasn't good enough. So to sum up, what was the roadblock and the challenges? We can make small interferometers. They have a short path length, so they have good coherence, but they tend to have Coulomb-dominated transport, large charging energy. If we make large interferometers, the coherence tends to be poor, and it's only going to be poorer as we go into high magnetic fields and in the fractional regime with multiple edge modes. But it does have the advantage of having low charging energy. So what we did is try to take the lessons from the early experiments and say, well, what if rather than putting a metallic gate with a lithography, we grow gates into the heterostructure layer? We have this MBE system. We can do all that. Let's make heterostructures where the heterostructure itself quenches the charging energy. Okay, and so this is the structure we started out with, this 30 nanometer gallium arsenide quantum well. That's the primary quantum well. That's where the 2D electron gas resides, the one we're interested in. There are barriers, these green layers that have high conduction band offset from gallium arsenide. So the electrons are stuck in there. But then nearby, about 25 nanometers on either side, flanking, we put additional quantum wells and fill those up with a high density of electrons. So what we do is, in the material itself, is make a parallel plate capacitor, and we quench the charging energy. There's two screening layers in close proximity to the primary two-dimensional electron gas that we want to study, and that really quenches the charging energy. It has some other very beneficial effects too that I'll try to describe, but this was our initial thinking. So if you look at the header structure, the Z direction is the growth direction. And the blue line represents the charge density. It's the charge density of electrons in the growth direction. Here's the surface, and we're going down into the substrate. And you see that the charge density in the primary quantum well is actually the lowest. It's 1 times 10^11. And on the two flanks, we have these higher density 2 digs about 30 nanometers away. The red line is just the conduction band profile in the vicinity of the surface. As you can see, that is what confines the electrons to these different layers. Okay. Now, that's great because we can quench charging energy. It makes it for a very complicated device. Instead of having a single 2D layer, in fact, we have 3 of them, all in parallel. And if you just look at the transport of that, it's a big mess. So we have to be a little bit clever in our device design and the fabrication that comes later. But you can do that. You can build a tiny interferometer here, and you can build gates and networks that will allow you to selectively cut off those other quantum wells, charge flowing through them, allowing them to screen but not to conduct, and that's how we operate the device. So what we do is build a device in which we have a tiny interferometer. This is the blue region is a mesa, with the green things are the ohmic contacts that take current in and out. All the other ones are gates. It's like a subway system of gates. There's gates below and gates above, and we can cut off the upper or lower screening layer, at least its path to the ohmic leads, at will. And with this network of gates, we can probe transport just through the tiny interferometer at the center on the mesa. That interferometer sees the 2D electron gases below and above it. It's nice and happy. It sees the screening potential of that. But far away, we can cut off the current path. So what we were able to do with the presence of these screen wells is make very small devices, about a factor of 20 times smaller than the ones Charlie was looking at, and improve the coherence because, for any number of reasons, but because it's a small device, path length. Now, there's other crucial factors I won't have time to go into, but these screen wells promote steeper confining potentials at the edge. And when you're dealing with this chiral edge modes, edge reconstruction and interaction can be a problem that is accentuated by soft confining potentials. So ideally, you want to have very sharp confining potentials that dictates the edge velocity and the susceptibility to reconstruction. So there's a lot of benefits to having these screening wells. So how do they work? Well, imagine you have a contact, it's shorted through all the layers, but you apply a potential to the top gate, you cut off the top screening one, well, you apply a potential from beneath. Now, conduction can only occur through the main quantum well. And so this is a technique that we borrowed from the study of bilayers back in the 90s and 2000s by Jim Eisenstein, looking at correlated bilayer systems. We just adopted it for our purposes. We have tri-layers. 20 minutes? Okay, I gotta get moving. But it's the complexity in the device is more than made up for in the physics it gives you access to. So I'll sort of truck along here. If I don't cut off the other wells, this is the Hall resistance through the system. It's messy and high density. I start cutting off the bottom well, I cut off the top well, and then you see the characteristic nice quantized plateaus showing conductance just through the main quantum well. Now, to tell you that I've really suppressed the charging energy, you can do an experiment. We can turn this into a quantum dot in the tunneling regime and measure Coulomb blockade spectroscopy. So here I'm comparing two structures, my device with the screening wells where I do these Coulomb diamonds. I don't know if you're not familiar with that. It's just spectroscopy that you do to see when you can move charge in and out of a quantum dot. And the charging energy for the screening well samples is quite small, about 17 micro eV. If I take the same device, same geometry, but put it on a heterostructure without screening wells, the charging energy is 200 micro eV. So I've really cut down on the Coulomb charging energy by a factor of 10, which has dramatic impact, okay? And it's quantifiable here. It also gives us a sharp confining potential. If you look at QPCs and look at how the conduction through them is changed as you apply gate voltage, say you're at nu equals 1, you have a fully transmitted mode with 1 unit E squared over H of conductance, and then it falls off dramatically. Other experiments done in materials without these screening wells have a more gradual fall off. So if you're at nu equals 1, you have approximately a unit of conductance, but it doesn't drop to 0. There are intermediate resonances and even intermediate plateaus saying that the confining potential at the edge is very soft, and you go through compressible, incompressible regions before you get to from the edge into the bulk, and those, of course, can complicate and obscure results when you're trying to do interferometry. So that just tells us that between the edge and the bulk in the interferometer, you want to have a sharp confining potential, not a sequence of gradually diminishing density where you see any number of additional quantum pulses. Okay, so we take that sample I just described to you and put it up at a fairly high field. It's whatever, 4.5 Tesla, nu equals 1. This is just the integer effect, and you see the lines of constant phase with negative slope, just as you'd expect for a case when the excitations are just electrons. The thing about this is very robust now because it's small and the coherence is high. The effect, the observation persists up to many hundreds of millikelvin, which is good by quantum Hall standards, and just means it's easier to see. Okay, you can quantify its coherence by looking at how the oscillation amplitude dies with temperature. You can find a coherence factor and extract an energy scale. And that energy scale at nu equals 1 is approximately 200 millikelvin. That compares favorably with earlier results that were a factor of 10. Okay, it's robust. You can see it at different integers, but that's just for completeness, not why we're here. But the degree of control you have is that you can selectively decide which edge state you're backscattering. So say you're at nu equals 3. You have 3 edge modes. I can partially backscatter the inner one, or I can fully backscatter and partially transmit the middle mode, or I can do it sequentially like that. And by doing differential conductance measurements, basically this kind of spectroscopy and looking at the nodal structure, I can say a lot about what my edge states are doing, their velocity, and therefore that'll determine the stiffness that we're talking about and the coherency. So I look for nodes basically by applying a finite bias, and I can extract the edge velocity. And this allows us to know a number of things, predict what the coherence will be, but also we can precisely say which mode we're interfering at any one time. We're not guessing. Okay, just these nodes tell you something about the velocity. That's where the cosine goes to pi over 2 and you get a 0. We can do it at nu equals 1, but we can also do it at 1/3. So we know how fast the edge is moving at 1/3 as well as in the integer regime. So if we take that device and move to the 1/3 state, all we did in this first experiment is crank up the magnetic field. Now we're up around 13 Tesla. You see that we actually have AB-like oscillations, lines of constant phase with negative slope at 1/3 filling. And as expected, the periodicity has changed by a factor of 3, consistent with now interfering not electrons, but E/3 quasiparticles. I can directly map the delta B to what I see at nu equals 1 and say there's a factor of 3. Of course, we can extract the charge, we get 1/3. So this was the first experiment in 2019. And in some ways, it was really nice. We finally got to see AB oscillations in the fractional regime. But in some ways, a little disappointing. Those phase slips that I mentioned to you, you don't see in this first experiment. You might notice the field range over which I'm scanning is rather narrow. It's not a wide range of field that's associated with the stability of the device. But this is important because I went to the March meeting in 2020 or 2019, and I was complaining or talking to Adi Stern and said, well, we see the oscillations, but we don't see phase slips. And he went away and thought about it, and pretty soon a paper showed up on the archive that seemed to be consistent with our results. So there's work of Rosenau and Stern that says why we might be seeing what we did. And the upshot of this is that there's a competition between keeping the system at constant filling factor, 1/3, by adding charge as you move the magnetic field around. That means not introducing quasiparticles, and the energy cost to create quasiparticles. And what we had done in the first experiments is so overcooked it, meaning quenched the charging energy so much that it was very easy for the system to stay really in the incompressible regime at 1/3, not create quasiparticles. It's easier just to add charge to the system and keep the filling constant. And if you do not add or remove quasiparticles, then you won't see the phase slips. So they actually went through, and you could say this B equals 0 is the center of the plateau. So the midpoint, that's when your chemical potential is in the transport gap. And until you move out into a regime where the chemical potential is in a region of higher density of states, where you start seeing the proliferation and creation of easily quasiparticles. And there's a critical point at which that happens. Of course, that's symmetric about the center of the plateau. So there'll be a region in the middle over which this system will stay incompressible. That's a very big difference than a lot of other interference experiments where for every time you change the magnetic flux, you create quasiparticles because they're the lowest energy object to create. Staying in this incompressible region actually turns out to be a benefit. The first experiment, we overcooked it, but we figured out how to correct that. And what they did is for this region of fixed nu, the incompressibility can be calculated by a few parameters: the gap of the state, which is large at 1/3, the filling factor, the effective charge, and this capacitance, this charging energy. And since we had made the capacitance so large, we really squashed this factor, and the denominator was small and the range was big. It was way too big for us to see anything. But that told us exactly what to do. Well, make the device smaller. We want a little bit of charging energy. We want to have a little competition going on, and make it lower density so that we can operate over a larger range of magnetic field under stable conditions. So what we did is made the device smaller. We reduced the density, and so that 1/3 occurred around 9 Tesla instead of 13 Tesla. That required a modified structure, but the idea is the same. And this is what you see. This is the first data we got. And you see the lines of constant phase with negative slope, but then you see these glitches. And at first blush, you'd say, well, that's just crap. That's noise. maybe it's electronic noise. But in fact, it's not. Remember, from the expression for the interference phase, there's the AB term, but also there should be phase slips when you add or subtract quasiparticles. Analysis of this data tells us both from the delta B and the delta VG that the fundamental charge carriers are 1/3 quasiparticles. Now, if you look at these lines where the phase slips occur, they're not random. They occur at very specific points in the VG plane space. And if you analyze the phase on both sides of any of these discrete jumps and then calculate what the discrete change in phase is, you get numbers that are surprisingly close to 1/3, delta theta over 2 pi, close to 1/3. Okay, so the discrete phase changes in phase correspond to minus 2 pi times, in our first measurement, 0.31. And so that's pretty darn close to minus 2 pi over 3. Their minus is because we're actually removing quasiparticles as we move up in magnetic field, or as we're removing quasiparticles. And the analysis we were going to do told us that this was consistent with the addition or removal of quasiparticles, and that the phase slip that occurred with them was almost exactly 2 pi over 3, as anticipated by theory. How much time?
10, 15 minutes.
Okay, plenty of time. Okay, so this was the 2020 work, and again, it was a modification of the heterostructure and device, but followed the principles of the first device and what we learned from the theoretical considerations of Rosenau and Stern. Okay.
So basically, each time your phase changes by 2 pi, you also add one anion. Is it the interpretation?
Not in the incompressible regime. These phase slips are actually associated with disorder. This whole region is largely in the incompressible regime. But of course, in real systems, there are potential fluctuations. And the disorder landscape, of course, has some noise to it. So the density of states is never truly zero inside the gap. And there are local regions in B and B where it's energetically, the quasiparticle, localized quasiparticle, is the energetically favored thing to make. If we were doing it all the time, you never see the discrete steps. They'd be occurring for every flux quantum you put in, and I'll show you how that happens in a second. So when you go outside the incompressible regime, that's when for every flux quanta you do create quasiparticles, and the behavior is quite different. So let me try to show you that. Okay, so there's a transition from incompressible to compressible regimes. Constant filling factor to constant density, just like I was describing before. So first, we just looked in this narrow region around the center of the plateau. It's funny, but it's the same data before. But now you extend out, and it dramatically changes. First of all, the lines of constant phase are quite diminished in amplitude. There's a loss of coherence. They also lose their magnetic field dependence. They become flat, where we have the lines of negative constant phase having negative slope. They flatten out here. And this is the transition region. This is about 450 millitesla wide. If you put in the numbers according to the Rosenau and Stern model, you get about 500 millitesla, pretty darn close for the incompressible regime. But out here, where we lose the magnetic field dependence and we lose amplitude, is where it's very easy to create quasiparticles. Every time I change my flux quanta, I introduce a quasiparticle. And of course, that can be a decohering process. If the quasiparticle number is not fixed inside the interferometer, the state circulating around see a varying quantum quasiparticle number, and it adds to the decoherence. Okay, so let me try to go through that a little bit. If you actually look at the numbers we extracted what the activation energy was, the gap. We know what the capacitance is because we measured Coulomb blockade, Coulomb diamonds, the quantum dot. We can put all these numbers into the toy model and get about 530. We measured the central region to be 450. Okay, so then you could say, well, okay, but shouldn't I have a finite periodicity once I go outside, like the original model showed? Well, there should be a transition to something from 3-knot periodicity to 5-knot, as it's easy to create quasiparticles. But in actuality, it's a little bit more complicated. The AB evolution is continuous. I build AB phase while I'm going along, but the anionic term is discrete. So what you might think is you see evolution, and then pops back up. Now that's thermally averaged. It looks like a flat line. And that's what we think we saw in this particular case. In fact, if the anionic phase is discrete, the quasiparticle number is thermally smeared in this particular experiment. The predicted temperature scale is about 4 millikelvin. Now we can get cold, but we don't have our electrons at 4 millikelvin. And so this was an issue here. Okay. Now, if you model this and just simple, this is modeling we did without theory help, very simple, and just look at thermal populations of what the change in conductance should be due in when you're at finite temperature, you should see at 0 temperature straight lines and this transition to these jagged steps, but it all gets smeared out as you increase the temperature. Okay. Oops. So our picture is in the center of you have the chemical potential where in the center where the density of states is extremely low. As you move out, you get into a region where the density of states is finite. You start getting appreciable quasiparticle generation that happens on both sides, and that corresponds to the different regimes of operation. Okay. Now, you might shake your head or say, oh, I'm not sure I get it or believe it, but I'm going to show you in a few slides that it indeed turns out to be true. So we actually look at the temperature dependence of thermal dephasing in the compressible and incompressible region. So if we're in the center of the plateau, even at 1/3, there's a temperature scale about 100 millikelvin. If we go off into the flanks, the interference is greatly suppressed. It goes down to by about a factor of 3 in this fundamental energy scale, saying we're rapidly dephasing. So in some sense, you can make a joke and say that this is an example of topological protection from dephasing because the large gap protects interference from dephasing, or as it's been deemed in the literature, actually topological dephasing, because the presence of these anions and their fluctuating thermal occupancy is the new dephasing mechanism. So if the interference phase is thermally smeared because we're in these different regimes, you could say that is itself evidence of the presence of anions. So topological protection or topological dephasing, it's up to you what you want to call it. Okay. But nevertheless, without trying to be too glib, the fact that you see differences is indicative in, I'm probably running out of time now, but I'll show you more tomorrow, of the presence of anions outside of the incompressible regime. Okay. And there'll be a 3rd and 4th experiment that I'll describe more tomorrow that will allow me to try to convince you of that with real data. So if I summarize the findings, these developments in interferometry goes all the way from materials to device path low temperature transport have allowed for the direct observation of anionic braiding statistics, something that we've been sort of waiting for a very long time. And one of my messages is to young people is novel header structures and device designs allow for new observables, new opportunities. So trying to be clever with devices and heterostructures can really be a good way to go. Now, the quantum Hall system in gallium arsenide, of course, is mature. We have these fancy growth techniques, can control it very well. We can do all sorts of fab and low temperature measurements. But I hope you'll see it as sort of a paradigm for what could be done in other newer interesting materials as well. The fact that using some basic ideas, you can get at some quantities that eluded us for a long time, I think bodes well, not just for, say, looking at non-abelian states in gallium arsenide, but also in graphene and many other structures as well. So hopefully some of the message will be translatable to other systems as they mature. So I think we'll stop here.
Any questions?
Well, there has to be experimentalists in the audience.
Thank you. What's the story for non-abelian anyons?
What's the story? Which example are you referring to?
Any, say 5 halves.
Well, 5 halves is interesting. There are some, I think the overwhelming body of evidence suggests that it's non-abelian. Identifying the exact topological order is a bit of a challenge. There's thermal measurements, thermal conductance measurements from the high bloom group that suggests one particular type of non-abelian order. They're not what you might expect from simple-minded theory. There are some interference experiments that are ongoing from Bob Willett and Bell Labs. We're working on it as well. We're building new interferometers that we think will be, or hope at least, will be very stable at 5 halves. There's interesting work in graphene. I think there's great hope for examination of 5 halves and non-abelian states in graphene because of they can generate larger gaps. They can get very high gaps in graphene. Of course, there's a higher magnetic field. And so, whether there's absolutely definitive proof for non-abelian braiding at 5 halves, depends on who you ask. I'm still working on it. So that tells you what I think. I'm still working on it.
I guess my question was more simple-minded. I was just asking, within this interferometer setup,
Yeah.
what's the smoking gun signature?
Don't ever use the word smoking gun. There's no such thing as a smoking gun in experimental physics. There's a preponderance of the evidence that builds up. You'll get in trouble saying smoking gun. Yeah, so you could, there are, in the interferometers, there is a very unique signature associated with non-abelianness. It's called an even-odd effect, depending on the parity of the localized excitations you have inside the bulk. And so there are theoretical predictions of what an interference signal should look like for 5 halves. And whether we've been able as a community to build interferometers working at 5 halves that display that is still not clear. I'm very hopeful. I'm going to continue working on it. Many of the problems that have been solved here for the abelian case are directly germane to 5 halves. 5 halves, you have intermodes, you have multiple modes, and you have to interfere in intermode, what might be considered soft, where the confining potential is soft. There are neutral excitations at 5 halves as well, multiple chiral Majorana modes. So a lot of the machinery that's been developed here, I think, will be directly applicable. Now, the question is, can you do all of this while maintaining a large enough gap at 5 halves so that the system is stable? That's the question. But there's no ambiguity about what to do, which is whether it can be executed. And there are other techniques as well. Interference is one, but thermal conductive entropy measurements, other types of conductance measurements can be brought to bear as well. I'm convinced that 5 halves will have some sort of non-Abelian order. Which one it is? Yeah.
Yeah.
Oh, there's a couple. You want to go first?
Yeah, so you mentioned that for nu equals 3, you can manipulate different modes, but aren't they equilibrated? So it would be like charge modes, neutral modes. So you can
Equilibration depends on a lot of things, but many different aspects, but I can preferentially backscatter different modes. I have control over. For the charge modes, I can see in the conductance measurement, in the QPC, which mode I'm backscattering, which ones I'm fully transmitting. So if you're nu equals 3 in the bulk, and you have 3 units of quantized conductance going through your QPC, that means all 3 modes are transmitted. 3 charge modes are transmitted. If I start introducing backscattering, what's called weak backscattering, the conductance will no longer be quantized. It'll be slightly below 3 units of conductance. That means I'm transmitting the 2 outer charge modes fully, and I'm partially backscattering the innermost mode. I can keep doing that until I fully backscatter, and then I only have 2 modes fully transmitted. So by looking at the conductance curves, I can tell you exactly, at least for the charge modes, what I'm doing. That's a really cool thing to have control over. You can tell what you're looking at. There's one more in the back, I think.
So to optimize your sensitivity on this jump in the phase, would you want the transmission coefficient to be larger or smaller as these QPCs? What's the right way to think about it?
Well, most of the theory is worked out in the weak backscattering limit. So the models are applicable when you're just inducing 10 to 20% backscattering. Obviously, you have to have enough backscattering so you see something, but the making connection between what you see in the experiment and theory is easiest when you're in the weak backscattering limit. So you always want to be as weakly backscattering as you can while still generating signal. I mean, there are theories for the strong backscattering limit too, but it's more complicated.
Yeah,
I have a question. Just out of curiosity, you're saying when you see the phase slip, that's the point that all the fractional charges are localized in percent. But could you estimate how many of them in this 1 by 1?
Sorry, you could estimate how many electrons are in just from the density and the lithographic area. But each one of those events is one localized quasiparticle coming in or out. So each one of those, I mean, they're all, that line you see that has those phase slips, that's just the position in voltage and magnetic field space where in that particular disorder realization, it's easier to introduce one quasiparticle rather than change the charge to stay at exact filling. So it's a countable small number.
So could you get like a number? Because naively from the formula, you get the n quasiparticle.
Yeah, that n is 1 in those cases because the phase slip matches up to the statistical phase. I can have examples where you have closely bunched ones and you can say, well, to be consistent, that actually, it's not, these are rare events. The ones I'm showing you, it's always the addition or subtraction of one quasiparticle. That's because mostly it's clean. It's mostly clean. There's only a few positions where there's actually energetically favorable.
I have a question, Michael. Yeah, I mean, can you again tell about the phase slip? So it's when you are sitting in a gap, right? So, and then you said that when you cannot add a quasiparticle because you're in a gap. I mean, is it
So there's a gap to, in a clean spectrum, you have ground state and then a gap to excitations. And you would say, well, okay, then there's no density of states in that region. But in real systems, of course, there's always disorder. And there's always potential fluctuations that give a small to finite density of states. So you could localize quasiparticles. You could have a localized quasiparticle in a particular configuration of this interferometer where that energy state to add the quasiparticle is lower than to add charge to the system to keep it exact filling. These are, but only in unique spots.
it's similar to kind of broadening in, I mean, in an integer quantum hall, as in you have broadened the ladder with
Yeah, there's some finite density of states. Here it's just small, and you only access a few of these in the range of parameters for your interferometer. If there were no disorder, I would not, if the potential landscape were perfectly flat, I shouldn't see those phase jumps unless I, perturb it with, say, a SDM, I'm making it up now, but put an SDM tip or something and perturb the potential to make a nucleation spot. What happens in reality, no matter how clean I make the samples, there will always be some random little slots like that in the system. And the interferometer just picks out a couple of those.
Thank you.
Last question here.
Luckily, they're small. That number is small and countable. If we're really just broadened and it was sort of continuous, I just smear out everything.
Yeah, just a question for curiosity. So, do you estimate physically how wide your 1/3 axis and how far from the edge?
How far from you can definitely look at the electrostatics to figure out how large the bulk region is. How far, over what distance does the density heal from the full background density to 0? So yeah, you can work out that. I don't have it on the top of my head, but that's all things we can know by measuring the area. We measure the area by going into the integer regime and looking at the AB oscillations for electrons. That tells you how much is depleted from the gate, the lithographic area, and that tells you where, over what length scale, the density has to go from full 2D density to 0. And the thing about these is that the bulk density inside the interferometer is the bulk density. It's the full density. It's not, if I took a Hall trace away from the interferometer, just in the bulk of the sample, and looked at the RD, the diagonal, essentially the RXY across the device, they'd overlap. It's not like they're separate regions. So yes, you can do that. And then we know, you can only make these things so small because then you can't be within a few magnetic lengths, of all that. So you have to have them so that the quasiparticles are widely separated for the stuff to work.
All right, one last big round of applause for Professor Manfra. With that, I believe we are done for the day.
Yeah, you made it.
Thank you.
Okay, how do I unplug? You want me to start on that so it's off?
Thank you.
Yeah.
That and then the clicker as well.
Yep.
Now some technical questions. So you try to make the device smaller to kind of minimize this charging effect.